we had the extension, well, not really extension problems, they're just more problems. So, and it's a good place to start because, we have a class of buffer between when we first talked about this and now, so it's definitely worth taking some time. So, f sub x, y, x, so it's a third order partial with respect to x. So first with respect to x, then y, then x again. Now on the previous page, I'm just transcribing this from that previous page. We determined for the same function that the second order partial with respect to y was equal to negative sine x cosine y minus e to the xy times xy plus 1. All right, that's relying on me having copied it down correctly, of course, but if we're going with that assumption, then at least we have a place to start, right? So the first question is just telling us to take the derivative of that with respect to x. So for the first part of the equation, that's not challenging because all I have to do is differentiate the sine, the sine part of it, because that's the part that's related to x. All right, so negative sine has a derivative of negative cosine. We leave the cosine y alone. All right, the second part, though, a little bit of a different story because it's a product of two functions, each of which contain an x and a y, which means that we have to evaluate this derivative using the product rule. All right, so first times the derivative of the second, so on. So minus, I'm going to leave that minus as an overall subtraction. First, e to the x times the derivative of the second. Pretty straightforward because on the inside there, whether you're taking the derivative with respect to x or y, you have a constant component, and the other part is going to clean up pretty nicely. All right, so really it's just this piece that I need to take the derivative of, which is just going to be y plus the second xy plus 1 times the derivative of the first, so e to the xy. Again, taking the derivative with respect to x is telling me that should give a multiplier of y, and that's because we're treating the y as constant. The derivative of x would go to 1 times y is y. Right? Close it up for the big old bracket, and that would be my derivative. Right? The unfortunate aspect of this is that I then have to take the derivative again with respect to y, which means that it's probably within my best interest to clean this up somewhat. All right? The good news is each part of the inner jammy here, the bracket, contains a y e to the xy, so I can pull that out of the whole thing. All right, so I'm going to clean that up a little bit first and write it as, so I'll still have my negative cosine x cosine y minus y e to the xy. I'm going to keep the brackets for posterity, I guess. 1 plus x y plus 1, which would clean up further to 2 plus xy. I could go regular parens now. All right, so it just begs the question of, is this the best form for the next step, in terms of housekeeping? Do we want to manipulate this further just to make our lives a little bit easier when we go to take the derivative in the next step, which would be with respect to y? All right, so this part, the first component, is not really concerning. Over here, it's a little bit of a different story because I have a y and e to the xy, each of which contain a y, and then this binomial that also contains a y. So my thinking on this would be to say, why not put that y back in so that I know I'm going to be stuck with product rule here, but at least in the product rule, I only have two factors. All right? Because if I left it in this current form, let's say I broke up my product based on these factors, y e to the xy and 2 plus xy. When I get to the part where I have to take the derivative of y e to the xy, it's going to be another product rule. So product rule within product rule, I don't like that. All right? In the case of the binomial, yeah, there might be product rule in there, maybe, but and there, in this case, there really won't be. But if there was, it would be a simpler product rule, and I'd be more keen on doing it that way. All right. So that's just my thinking. You can do it any way you want, but that's where my brain takes me. All right. And as you know, my brain is an interesting place. It doesn't always take us where we want to go, but it tries. It tries its best. So anyway. Derivative of cosine is negative sine. So we're looking at negative cosine x times a negative sine y. So cosine, I'll write the cosine first. Cosine x sine y minus, so I'm going to do the same thing as before. First times the derivative of the second, e to the xy, times the derivative of the binomial. Now, again, it's with respect to y. So in this case, the 2y becomes a 2. The xy squared, I treat the x as constant. Y squared becomes 2y, so 2xy. Plus the second times the derivative of the first. And the derivative of the first is really just going to follow the same format as before. So e to the xy multiplied by the derivative of the exponent with respect to y, which is just going to be the x. So e to the xy times x. Oops, just tuck that over a little bit, and there it is. All right, so pretty nasty. I mean, we can clean it up further, but there is really no benefit to doing that because we don't have an objective reason to do so. Do I need to set equal to 0 and solve like we would in Calc 1? Do I need to find yet another derivative after this? None of that is part of this. So I have what I'm looking for, and I'm comfortable with that.
Is there supposed to be a negative for cosine?
There was, but cosine y became negative sine y, so that offset that. All right. So yeah, it's got some beef to it, but if you're systematic about it and you approach it in a reasonable way, it's not too bad. The next one looks kind of funky, but in a lot of ways it's easier. So I'm going to rewrite it though first. I'm just going to write f. xyz to the 1/2 power plus x squared y cubed z to the 4th. And so I want to differentiate this with respect to x first. Then that result gets differentiated with respect to y, and so on. All right, so partial with respect to x. Well, x is tucked inside another function, so it's chain rule. So 1/2 xyz to the negative 1/2 times the derivative on the inside. Now the derivative on the inside is only related to the x. Everything else is treated as constant. So the derivative of x would be 1.
For the square roots and stuff, can't you take the x and the y and the z out?
You could. So the derivative of x, y, z would just be yz because x goes to 1. And then when we take the derivative of the other part, again, I mean, it might look like product rule, but y and z are treated as constant. It's only the x that's variable. So we're looking at 2x y cubed z to the 4th. All right. So then, little housekeeping. I think it's definitely worth your while when it comes to problems like this, before moving on to the next step, to clean it up a little bit. All right, so we're looking at yz over 2 root xyz plus all that other stuff. Now, we can simplify this a little bit. The yz will divide, you could divide that by the root of yz. All right, so we're looking at the square root of y, square root of z, over 2 root x. All right, plus all that other stuff. All right, now it's up to you how you want to go about it at this point, but I think it would make sense to first consider what it is you're taking the derivative with respect to, because in this case, we want to take the derivative with respect to y, so that means everything else is constant. So what I would do is rewrite this, treating everything else as a coefficient of y. So I would have my z as a root, I'd have 2 root x, and then I would write the y to the 1/2 power. All right. So then when I differentiate, I'm just applying the power rule for y. I'd be looking at, so f of x, f sub xy, I'd be looking at root z over 4 root x, y to the negative 1/2, plus the derivative of the rest of it. So again, it's the y stuff that's variable, everything else is constant. Derivative of y cubed is 3y squared, so we'd be looking at, so plus 6x y squared z to the 4th. All right, so again, we're just taking the derivative of this part of it because everything else is held constant, and then multiply that result against everything else. All right. So then we can clean it up a little bit again. Again, it's worth your time to do that. We have root z over 4 root xy plus all that other stuff. Yeah, now we're going to pull the z out. Right? That z I can think of as z to the 1/2, and everything else is a coefficient. So I'm looking at 1 over 4 root xy z to the 1/2 plus all that other stuff. And then I could differentiate. And again, once you get to the derivative, that last part, f sub xyz, so the third order partial with respect to z, you don't have to worry about simplifying it because we've gotten where we needed to get to. All right, so that's 1/8. Well, let me keep it with the radical. xy, z to the negative 1/2, plus, so it's the z to the 4th that's getting differentiated to 4z cubed, so 24 xy squared z to the 3rd. All right, and so, I mean, if you felt the desperate need to clean it up as much as you can, then you might say 1 over 8 times the square root of xyz plus all that other stuff. But that would be your third order partial with respect to z. All right, so it's got some oomph. Just lots of writing, really, and organization more than anything else. Because really, what did you do more than just apply the power rule repeatedly? I mean, at least in the last one, you did some product rule. There's no advanced level calculus in here. It's just a matter of keeping things organized. And very easy for things to slip through the cracks. So just got to be careful. Little notes to yourself sometimes help. All right, the last question there is a word problem. But
I don't think we got to B.
what's that?
I don't think we got to B.
No.
Yeah, this is new.
Yeah, I'm just debating whether or not I want to do it right now.
Oh, okay.
It's supposed to show how each variable affects the other or something?
Yeah, there's a relationship in there. I mean, it really just amounts to, it's sort of like a throwaway problem. I'll just give you the gist of it. I mean, there's a meaningful application to it. It's just we're never going to get into it, so it questions the importance. But basically, it's saying find the partial of S with respect to L. Find the partial of S with respect to W, and the partial of S with respect to H. And just note the relationships that exist. All right, so I don't know. It's not very riveting.
It's pretty easy.
Yeah, I mean, easy's good. We like easy sometimes. But maybe I'll just put a star on it.
That was a little bit too easy. Question for yourself.
Yeah, I'll put a star on it. You can check it against the key, I guess. If you're gonna ever have a hope to actually visualize them, they can't be too crazy in terms of the structure, because if I handed you a cosine x sine y minus e to the xy, like, okay, cool, it's fun to take a derivative of something like that, but I could not, with any good conscience, turn around and ask you what that would look like graphically, because I don't know what it looks like graphically. I would have to go to GeoGebra. But for other surfaces like this x squared plus y squared equals z or something like that, there's a reasonable expectation that you could figure it out, right? So, but in this case, it's still not too bad. I need partial with respect to x and partial with respect to y, right? So I can just kind of chuck that in over here. So I will do partial z with respect to x. All right, so that's going to be 2x y squared. The 1 goes away. Partial z looks too much like a 2. Partial, still. Bring it in, yeah. Oh, that looks terrible. Partial z with respect to y. 2yx squared. Or 2x squared y if you want. Doesn't make a difference. All right, so we need those. You could use the alternate notation if you want, but it was written as z, so I figured it'd go that way. So we want the equation of the tangent plane and the normal line to the surface. All right, so, well, I suppose I should highlight the tangent plane relationship. In both cases, whether it's the tangent plane or the normal line, all we're doing is evaluating our partials for the particular coordinate. All right? Which is not hard. All right, so let's take a look at 1, 1. So at 1, 1, we have an a value.
Is that supposed to be a 2, or are we doing the weird D's?
Weird D's. Yeah.
The weird. I don't know how to phrase that. It's not supposed to be straight.
We're doing those points for both partial derivatives.
Correct. All right, so partial z with respect to x at 1, 1. That's the same as saying partial x with respect to partial with respect to x at 1, 1. Either way. And this is really just my license to ditch this notation and go with that notation in a second. But x and y squared are both 1, so this is just going to be a 2. All right. So partial z with respect to y at 1, 1, same as partial with respect to y, 1, 1, also going to be 2. All right, so not bad. I also need to know f of 1, 1. So I need to know z at 1, 1, which is the same as f of 1, 1. So that goes right into the original function. So it's just, well, a 2 again, right? A lot of 2's. So we have everything we need to write the equation of the tangent plane. So z is going to be equal to our f of a comma b, which we already figured out is 2, plus the partial with respect to x times x minus a. So that's a little twist on it. But
Times 0.
times x minus, the a value is 1. Plus 2 times y minus also a 1. All right, the b value is 1 also. All right. So then we want to clean it up. So we're going to have 2 plus 2x minus 2 plus 2y minus 2. And some things will clean up even further. So we'll have some things cancel out here. Get rid of those two guys, I guess. So let me just bring it back up here a little bit. We would say 2 equals 2x plus 2y minus 2. And really, it just depends on how you want to write it. You know, like if you want it in z equals form, or if you want it the way we learned about it in the last unit, which is x, y, z equals whatever the d is. So in this case, you might say 2x plus 2y minus z equals 2. That would have been perfectly fine also.
Is there like any reason why we derive something like that, or is that something just to remember those equations for z, for the tangent plane, x, y, and z for the normal line? Do we just remember that, or is that?
Yeah, you just remember that. I mean, we'll derive it on, when we get the chance next time I'm here.
But it's not something that.
But it's not something that I'm going to ask you to do. But it does add a little insight as to where these formulas are coming from, which I think is definitely meaningful. All right, so let me just write these down so I can go to the AR app, see if it actually works. Maybe we'll just do it all in one shot. I think, I don't know if the normal items are going to come up very easily. On the AR app, I might have to go to regular GeoGebra, like slum it.
But for the normal line, are you supposed to do all of them, x, y, and z?
Yeah, because it's a parametric equation. So normal line in 3 space would have the 3 components. All right, so we need each one of them. All right, so the a value is 1 plus partial with respect to x we figured out is 2. So 1 plus 2t. Y is 1 plus 2t again. Made up of the same ingredients. And the z is your evaluated value. So in this case, again, 2 minus t. All right. And again, I'll give you a sense of where that came from next week, hopefully. So you just got to keep things straight. All right, so what I want to do here is find dz dt, knowing that I have a function of z that's in terms of x and y, but then those x, y variables are also themselves functions of other variables, right? In this case, another variable, t, right? So I need to find dz dt. Now, if you think about this reasonably, using a systematic approach, you'd come up with the idea that, all right, if I'm using partial derivatives, I could find the partial with respect to x. I could also find the partial with respect to y. I'll leave a little space and write or. If I find the partial with respect to x, I could then find the derivative of whatever that x function is with respect to t. All right? Looking at that x function, you could see it's a function of one variable. So it's not, there's no partial derivative there. You need to have functions of multiple variables in order to say that you're taking a partial derivative. So it would just be dx dt. The other possibility is if I took the partial with respect to x, it could be the case that I need to find the derivative of y with respect to t. All right, again, because y is a function of t, not a function of t and some other variable, just a function of t, so it's ordinary differentiation. Right? The or here is the way we would think of or in a stat class. In fact, there's a lot of overlap between this course and statistics when you really think about it. Or is talking about addition, right? So if you're thinking about like probability, probability of this or that happening, you would add the two probabilities together. It's the same idea here, right? So I'm going to take the partial with respect to x, multiply it by the derivative of x with respect to t, and then add to that the partial with respect to y, multiply that by the derivative of y with respect to t. All right, so basically I'm just trying to figure out all the different pathways that I could end up with a dt, starting with a z. I can go the y route, or I can go I can go the x route, or I can go the y route. If I go the x route, then I have to multiply by dx dt. If I go the y route, then I have to multiply by dy dt in order for that pathway to take me all the way down to a dt. All right. What does that mean? I need these ingredients. Is that hard? Well, it depends on the function. All right. So in the case of the x and y functions, it's not hard at all because dx dt, I just chuck that in right here. 2t. dy dt, cosine t. The partial is a little bit of a different story. Still not difficult because even though it might look like it's a product rule situation, it's not, because we have x squared, that x squared being one factor is only containing x's. The e to the y, the other factor, only contains y's. If a factor contained both x and y, it's a different story. But here I'm holding the y part constant, taking the derivative of the x part. So 2x e to the y. And I'm going to multiply that by dx dt, which is 2t. Plus. Mm-hmm. Yep. Partial derivative with respect to x, yeah. So derivative of x squared became 2x, and I'm leaving the e to the y alone. dx dt I got from here, which is 2t. Partial with respect to y. I'm leaving the x squared alone, and I'm taking the derivative of e to the y, but e to the y has a derivative that's e to the y. So nothing changes for that one. X squared e to the y. And we know dy dt is equal to cosine t. so that is how we would define our derivative of z with respect to t.
So are we going to sub in the values now, or?
We can. We don't need to, though.
What was that part of it? Then you can either use either of the two of finding the derivative dz over dx, dx dt, or dz dy dy dt. You have to use both anyway.
Right. Well, it's the math or, which is the one that, it's like in real life, or it implies you have a choice. Math or, you include them both. You know. I still have to fight that battle with my Algebra 1 students, where we're solving quadratics, and the answer is 2 or -1, and they just want to put down one or the other. And I'm like, no, it's either of those satisfy the idea of the derivative with respect to t, in this case, and so we have to include them both as part of our possibilities. Just like either a red ace or a black jack would satisfy my requirement to get a sum of 21 in the game of blackjack, for example. You know, like I would take all the cards that would satisfy my requirements, add them all up together, and then that would give me what I was looking for in terms of a probability. Okay, so it's a complete collection. It's not a choice, unfortunately. Because otherwise, I would just choose the easier component and just go from there. So it kind of defeats the purpose of doing it this way if you had to then substitute for every x and every y what they truly are. But it's kind of implied that in a lot of cases you should do that, but it does depend on the instructions. Once you have, well, just be careful about the instructions, because once you have a derivative, you have a result that is equivalent to the correct answer. It's just a question of the appropriate form, right? So I could go through and replace every x with a t squared minus 1 and every y with a sine of t. That would make it a little bit nicer because it would be entirely in terms of t. This would be equivalent to what you would get if you initially replaced your x's and y's with t squared minus 1s and sines of t's, and then took the derivative. This, in theory, is supposed to be an easier approach. Right? It allows us to take something new that we're learning, apply it in a way that takes something that would be in Calc 1 a pretty challenging, or could be a pretty challenging derivative, and simplifies it a little bit. Right? In that context, it makes it an optional approach. In this context, you're taking it and making it into a really convenient way of doing things. Right? Again, without context, you don't know what the best way of representing an answer is, short of being told what way to represent that answer. Right? So just be on the lookout for the instructions. Another word problem that we'll skip for now. That one actually should come a little later. So if somebody wants that for a typo, you're welcome to it.
Is this supposed to come later?
The Cobb-Douglas word problem.
Okay.
That should actually come after this chain rule. I like to do the applications after I cover a topic. It's kind of nicer that way. All right, so sometimes you have a function in terms of two variables, and those, so in terms of two variables, and those two variables are themselves functions in terms of two other variables. All right, so not x of t, y of t, but x of st and y of st. A little bit of a different story now, right?
So a chain rule inside of a chain.
Chain rule inside of a chain rule. That's like 16
Partial
walls.
derivative inside a partial derivative. It's a partial derivative.
Fourth wall break inside of a fourth wall break. It's like 16 walls. So when I want to find partial z with respect to s, what I got to think about is the different ways in which I can get from z to s. All right. So I got x's and y's, right? That's where I have to start. So I could do a partial z with respect to x, or I could do a partial z with respect to y. Then I could do, well, now it's partial with respect to x. From there, I could do partial x with respect to s, or partial x with respect to t. The same idea for the y's. All right, this is all coming from z. So a little tree diagram action. Pathway here. All right, so what I'm looking for is partial z with respect to x. Then what I want to do is follow any pathway that gets me to an s. Partial z with respect to s. Any pathway that ends with an s. All right. So that would be this branch and this branch. So my partial z with respect to s would be partial z with respect to x times partial x with respect to s plus, because it's an or situation, it's either I'm going to follow this pathway or I'm going to follow that pathway. Either way, I'm going to get to a partial with respect to s. So then partial z with respect to y multiplied by partial z with respect to s.
Now your y with respect to s.
Yes. Thank you. Now, so now I have the roadmap. I'm going to follow it. I need a partial z with respect to x, which means I'm going to work with the original function. So z is equal to, I'll write it as x squared over 4 plus y squared to the 1/2. I need both first order partials, so I might as well just bang it all out. (1/2) x squared over 4 plus y squared to the negative 1/2 times 1/2 x, 2/4 x to the first. There.
So when we had z, we broke it down to partial z divided by partial x times partial z divided by partial y to get the fourth thing below it, and then we're breaking up partial x divided by partial s again, and this is where the black row comes from.
He's referring to the diagram.
Oh, the diagram, yeah. So
I'm just confused how we got the dz divided by, partial z divided by partial s. Yeah, to get that whole row.
No, he's not saying divide.
oh, here.
Yeah.
Oh,
What
this
was the
expanded
partial derivative
into
of
that.
z?
Yeah, the partial derivative of z with respect to s is the consequence of this diagram,
Mhm.
which is this times this plus this times that.
Oh, that's what it was. Okay.
All right, so we'll clean that up. Really not much to clean, though. So x over 4 root x squared over 4 plus y squared And you know, maybe that wasn't worth it. We'll see. Maybe we don't need to clean it up like that. Partial z with respect to y. Same jazz, at least to begin. So we're looking at y over x squared over 4 plus y squared. All right, 2's would cancel out. That radical is just going to the bottom. All right. The other part should be a little easier. I mean, maybe not. It's not guaranteed, but usually the inner functions are not too bad. But these are going to involve some product rule. Maybe. We'll see. Actually, I think we're all right. All right, so I'm just rewriting it so I can scroll. So I need partial x with respect to s and partial y with respect to s. Yeah, it looks like we don't need product rule. I looked at it too quickly because we're holding 2t constant. We're just taking the derivative of cosine s, which is negative sine s. So negative 2t sine of s. And then for dy, or partial y with respect to s, holding the t constant, taking the derivative of sine of s, which is cosine s. So t cosine s. All right, so it's just a matter of putting it all together now. The fun times. So partial z with respect to s. Multiply these two together, multiply these two together, add them up. So negative 2, all right, xt sine s over 4, which we could clean up, times the square root of x squared over 4 plus y squared, plus yt, 800, cosine s, over the square root of x squared plus 4, x squared over 4 plus y squared. All right. And again, the only thing that we could probably address here is that the 2 and the 4 can divide, making this, instead of 2 over 4, 1 over 2. So I could write it like that.
So we definitely don't want to send the x and y values.
No, definitely not. Definitely not. But you can be satisfied with the knowledge that had you gone back to the beginning, look at all this, substituted in to the original function, and then taken the partial derivative of that with respect to s. So basically replaced your x's and y's with 2t cosine s's and t sine s's. Simplify, clean it up, take the partial derivative of that with respect to s, you would have gotten something equivalent to this answer. Right, and that's all we're really after at this point.
But now you would have asked the partial derivative of z with respect to t.
Right, which is what I'm going to
Which is
put a star on for you. But basically, it's starting the whole problem again. This part is the same. These two, you're taking the derivative with respect to t instead of s, and then multiplying it again. Now, do you have to start the problem over again? Of course not. Okay? On a test, though, if you're given these parameters and you're just asked for that, you have to go the distance because you wouldn't have all this information already. But for you to tackle that part of the problem, the only thing that's going to change is this part. Partial x with respect to t, partial x with respect to, partial y with respect to t, and then the way you multiply it. All right, so it's a much easier road to hoe at this point because you don't have to do all that work. But it's still worth your time to kind of play around with. All right, so that was page 60. The idea being that we've seen unit vectors before, and we could also think of u as being equal to cosine theta sine theta. Not really sure why I chose to write it there as opposed to below. I guess it doesn't really matter, but what's happening is you're taking really the dot product between the partial derivative vector and the unit vector. So just kind of off on the side here, I'll show you. If you have a vector containing your partial derivatives and you dot that against u, that would be the same as dotting it against cosine theta sine theta. All right, so that first line, that directional derivative, d sub u, is really what you would get if you just did the straight multiplication, leaving it in terms of u, all right, because u is u sub 1, u sub 2. If you dot it, that's what you would get as a result. But you could also get an alternative form, which I think is a more useful form, that involves the angle. Now, you don't always know the angle, but when you do, it's very meaningful. So we would say partial with respect to x cosine theta plus partial with respect to y cosine theta. Cosine theta, sine theta. All right, so at this point, we're just focusing on skills. So what we want to do is find the directional derivative of each function when you have a given angle of theta. All right, so I have a coordinate, I have a function. So I'm going to find the partials. Partial with respect to x is just 2x. Partial with respect to y is just 2y. But I also need it at the particular coordinate. All right. When you're subbing in values, remember it's only the relevant values that you plug in. There's an x value and a y value. All right. So if I plug in the x value here, I'm going to get a 4. And if I plug in the y value here, I'm going to get a 2. All right, so my directional derivative, d sub u, in the direction of unit vector u, of function f at coordinates 2, 1, would be equal to, we could say 4u sub 1 plus 2u sub 2, but we have an angle. So this would expand to 4 cosine theta plus 2 sine theta, which in turn would become 4 cosine, because they told us the particular angle is pi over 4, plus 2 sine of pi over 4. All right, so cosine of, yeah, so square root of 2 over 2 in each case.
Hard for this quiz.
Ready to rock and roll. So 2 root 2 plus root 2 is going to be equal to 3 root 2.
That's what I thought when you said that. I was like, okay.
Really? An hour ago.
I've been there before.
Okay,
Nah, it's the same intentions.
All right, so this is what we're calling the directional derivative at the coordinate where x is equal to 2, y is equal to 1. There's a z associated with that. You can figure it out. Maybe just 5. So if you're looking in 3 space, it would be the coordinates 2, 1, 5. Going off at an angle of pi over 4 from that direction, you would have a magnitude of 3 radical 2. So that rate of change would have a magnitude of 3 radical 2. All right, so that's what a directional derivative is telling us, is that you have a vector going off from that coordinate or those coordinates at a particular angle. This is what the magnitude of that vector would be. All right, so the rate of change, instantaneous rate of change if you want, thinking back to Calc 1. All right, so the second example follows the same suit. It's nothing more challenging, so I'll just pop a star on that one. So then we get the gradient vector. Now the gradient vector is really not any more challenging. The good thing about this is really you're just looking at a more generalized version of a directional derivative, because you're talking about the partial derivatives just written in vector form. So not particular values, but general forms. And so there's a blurb here. In most cases, there's one direction u where the directional derivative is the largest. This is the uphill direction. All right. But if you're at the top of the mountain, then that might not be true. You know, so you're thinking of surfaces. If you're at the top of the mountain, there would be no uphill from there. The only place you can go is downhill. So what happens is you end up with little micro movements from point to point as you move along a surface. So the gradient tells you the movement that involves the maximum rate of change, so the maximum slope. All right. So if you're trying to, let's say, climb a mountain and you want to have the most direct path there, you might say, well, I'll just go that way. But if there's a lot of twists and turns along the way, that could be a problem. Right? What the gradient does is it gives you a sense of what direction you should go in order to maximize your productivity, basically. Right? So the slope should be the greatest in order to have the most movement. Right? So, but the thing is, it's not always going to be true for all cases. So if the surface is not constant, then you can't assume that the rate of change is going to be the same for the whole trip. So maybe you take one step, and then you have to do a course correction. Then you take another step, and you have to do another course correction. So it can be kind of tedious and troublesome, but what the gradient really requires you to do is make a determination of the best path to take on a micro level, then start following that path for a smidge, then recompute the gradient at that new location to give you the new direction that you should follow that path for a smidge, and then recompute, and then follow that path for a smidge, and so on. So you might have these little micro paths that you're taking. Ultimately, it gives you the path of steepest ascent, gets you to the top of the mountain, but it doesn't seem like it's an effective way to do it, especially if you're stopping every 2 steps to whip out your calculator to figure out what the best path to take is. When in reality, you're like, that looks steeper than that, so I'm just going to climb that, you know? So common sense kind of kicks in, but the idea is that there is a mathematical approach that can be followed, right? And so that's where this comes into play. Right? So that's what all of this is saying. How do you find the gradient? Well, you find, well, this looks familiar, your partials. So upside down triangle. Yeah, there's a name for it.
That's what it's called.
It's called an upside down triangle. I believe NAMBLA?
So upside down triangle.
Yeah, we're going with upside down triangle because I saw that South Park episode.
Oh my god.
So
That's funny.
Wait, which one?
It had to do with the food pyramid.
Skip the calendar.
Oh, yeah.
There you go. That's so
So yeah, that's how we're gonna do it. But again, if you
Illuminati.
if you look at what we're doing here, it's really just partial with respect to x, partial with respect to y. Put it all together, and you have your gradient. So 2x plus 2y.
Del.
It's del.
Del.
Yeah, for short.
Del.
Yeah, it was nice.
Oh, that's it.
Yeah.
So what happens when we take the second gradient? What if we take the gradient of the possible
2i plus 2j.
This is just del.
It doesn't have the same meaning. Right now, we could find, it's not asking for it, but we could find the magnitude of this.
It's just going to be
Because it is a vector.
it's just going to be 2 times x squared of x squared plus y squared.
Alright, so, I mean, if you really want to get fancy, you can go back and substitute it in terms of the original function. You could say 2 root z, but that's not really necessary. But and again, this was not really asking for this, but there is a consequence of the it's written here. Maximum rate of change of function f at AB. If you have the magnitude of your gradient, it occurs in the direction of the gradient. Right? So whatever the direction is, the directional derivative at this point, or whatever coordinate, its maximum rate of change will occur with this value in whatever that direction is. All right? So all of these properties come into play, so it's a nice little feature related to the gradient. The minimum rate of change occurs in the direction opposite of the gradient. And then you have some things related to orthogonality, but we'll get to that down the line. So, tackle a problem. Number 2 is pretty much the same thing. For number 3, it's saying, is there a direction u in which the rate of change of the temperature function given at is, and then give reasons for your answers. Jeez. So, function of 3 variables, so that's something to keep in mind. I need my partials. So we're looking at 2y, just 2y, right?
Yeah.
And then 2y, or I'm sorry, t partial with respect to x at the coordinate 1, negative 1, 1 would be equal to negative 2. Partial with respect to y would be 2x minus z. So 2 minus 1, I believe, is 1. And then partial with respect to z. That's just going to be a negative y, right? All right, so what I'll do is I'll come up with the gradient vector, just because we covered that, might as well. got three components. So 2y I plus 2x minus z j and then plus yk, so I'll just say minus yk. Now the magnitude of this could be complicated if I were to actually do it in algebraic form, but since I have it at a particular coordinate, I can figure out the gradient at that location. And we've already figured out these numbers. -2, 1, 1. So plus k. Then I would want the magnitude. So it looks like √6. Square root of 6, what's that approximately? Root 2.7?
No, I said 2 point something.
2 point something.
I would assume.
I would assume also. Does anybody have something other than 7?
2.45.
2.45. All right, so we just figured out two things, one directly and one indirectly. We figured out, well, they were asking, is there a direction in which the rate of change of the temperature at this location is -3? So could I go off in a particular direction and have a rate of change be -3 degrees Celsius per meter, all right? And what we got here was the gradient value at 1, -1, 1, right? What this gives is the maximum rate of change. At 1, -1, 1. So if I were to take off at any direction from 1, -1, 1, the most rate of change that I could accomplish would be 2.45 degrees Celsius per meter. Right? I didn't include the units. But one of the properties tells us that the opposite of that would be the minimum rate of change. The negative magnitude of the gradient is the minimum rate of change. So what it's telling us is that no matter what direction I go off in from the coordinates 1, -1, 1, following the surface, I can achieve a maximum rate of change that is no greater than 2.45 and a minimum rate of change that is no less than -2.45. Right? Everything has to be in between. All right, so what we created were constraints, and so therefore cannot reach 3 degrees Celsius per meter. Negative?
Yeah.
Negative. All right, well, or positive, doesn't matter. But the question was asking negative, and so it is true that we could not ever get to a -3 measure because the lowest we could ever get to is -2.45. All right. So the next one, I'm going to put a star on that because that just expands it to three variables, which we really just did. This was the prelude to the rule, and 4 is just an extension of that. So that should be fine.